welcome everybody. Today's afternoon session. Tibor Rakovszky from Budapest University of Technology and Economy will present his work on finite temperature quantum topological order in 3 dimensions.
Right, thank you very much. So what I will tell you about today is a system that exhibits topological order in the way that you've heard before, not just in its ground state, but also at kind of finite but low enough temperatures. And this is, in fact, the first example of something like this that we know of that exists in kind of physically realistic dimensions, in particular, 3 spatial dimensions. All the previously known examples require you to go to at least 4 dimensions. So just to motivate this a little bit, let me mention 2 motivating questions that kind of tell you how this fits into the things that were discussed last week. So last week, you heard a lot about this idea of classifying phases of matter at 0 temperature. This is something that Vijay talked about on Monday, that we can think about kind of ground states and try to classify them into various equivalence classes that can be smoothly deformed into each other without closing the gap. And you also heard that there's this very rich theory of how to classify these phases using anyon theories and fusion categories and so on. And the reason we care about ground states is because they describe what happens in anybody's system if you cool it down to absolute 0 temperature. Then you are just in the ground state. But of course, we are never actually at exactly 0 temperature. We are always at some finite temperature, even if it's low in many cases. So the natural question to ask is, do these different phases survive if you go to finite temperatures? And what has been known before is that there are examples that indeed survive at finite temperatures, but they all require, all the known examples, physical dimensions, spatial dimensions that are 4 or larger, which is kind of unphysical. It's not something that you would actually see in a condensed matter experiment. Maybe in some like artificial synthetic system, you could do it. So there's kind of an open question of, can you do something at finite temperature in 2D or 3D? Now, there's another way of approaching this problem, which is that finite temperature states are mixed states. They are not pure quantum states. And as you heard from Abhinav on Friday, there is this kind of newly developing theory of intrinsically mixed state phases, kind of new phases that only exist at mixed states. So now you could ask a different question, which is, can these occur in thermal equilibrium? Like the scenarios that Abhinav described are kind of more these synthetic quantum systems where I can engineer lots of things. I can engineer some sort of dissipation to create a particular quantum state. But do you get these new mixed state topological orders in this sort of more conventional condensed matter setup where I just have some material, I stick it in a fridge, cool it down? Can I get that? So what we showed is kind of an answer that ties these 2 together, which is that we have an example of a system where we do have some non-trivial quantum topological order at finite temperature, but it's not a pure state topological order. It's kind of one of these intrinsically mixed topological orders. And so what I mean by topological order for the purposes of this talk is that the system has some sort of long-range entanglement. So that there are some correlations which are both genuinely non-local, but also genuinely quantum. They are not classical correlations. And I will define this more carefully in a few slides. And the statement is that you have a system where such correlations exist in some finite range of temperatures, below some critical temperature. And the key kind of new ingredient that allowed us to do this is that this will be a system which have emergent fermionic local quasi-particles that have a fermionic braiding, even though the kind of underlying microscopic degrees of freedom are all bosons or spins. And that will be a kind of a key feature. And there is also an important caveat, which is that there are different ways you could define finite temperature topological order. One is this entanglement definition that I just gave. But another thing that you might want is a system that is a passive quantum memory. And I will define more carefully what that means, but it's something that kind of is able to preserve quantum information in its thermal state. And this will not be achieved by our example, just to preempt some questions. Okay, so just to kind of set up some language, let me start where a lot of the other speakers have started, which is reviewing the 2D toric code. So 2D toric code, we are on a square lattice, qubits live on edges. You have 2 kinds of terms, vertex terms and packet terms. And correspondingly, we have two kinds of symmetries that you can construct out of these, which are products of Z along the loop or products of X along the loop on the dual lattice. And these all commute with the Hamiltonian. So you can think of these as this kind of one-form symmetries of the model. And then you can think about the corresponding excitation that you get by opening up these loops. They have open lines, they create excitations at their endpoints. And these excitations have some non-trivial braiding. There are two types, E and M. If I take an E around an M, I pick up a -1. And in terms of symmetries, you can think of this as a kind of mixed anomaly between the two symmetries. This is analogous to what you heard about in the morning talk this morning, except this is for Z2 symmetries rather than U1 symmetries that you have in electrodynamics. And another property is that if I take the system on a torus, periodic boundary conditions, there are multiple ground states, which you can think of as a spontaneous breaking of the symmetry. The symmetry takes you between different ground states. And so why are we interested in this model? The sort of traditional motivation is that this is a toy model for certain zero temperature phases of matter, certain spin liquids that you could see in like an actual material. There is also a kind of more modern perspective that Michael mentioned last week, that there are these synthetic quantum systems, things like Rydberg atoms or superconducting circuits where you can kind of realize this kind of system. So I mentioned long-range entanglement before. Now I can kind of define what I mean by this, which is the following. It's most easily defined by what it isn't, which is a short-range entangled state. So a short-range entangled state is something that I can prepare in the following way. I take a trivial initial state, some completely kind of uncorrelated state. And then I evolve this uncorrelated state with a local Hamiltonian for some finite amount of time. Or in a more quantum information language, I apply some finite depth circuit of local unitary operations to this initial state. And this finite depth circuit, it can create some correlations kind of locally within the light cone of this circuit, but it doesn't create any long-range correlations. So kind of long-range, this is a trivial state. And then a long-range entangled state is something that I cannot create with this procedure. And the statement is that the ground states of the toric code are indeed long-range entangled. And there's a particularly sort of strong form of this statement from this paper last year, which says that if I take any short-range entangled state that I can prepare with a circuit whose depth is some number t, the number of layers is t, which you can think of as the time of how long I evolve, the overlap with the toric code ground state is going to be exponentially small in the ratio of the system size L and this parameter t. To get any kind of reasonable overlap, you really need this t to be the size of the system size. You have to create correlations throughout the whole system. And there's a nice picture of how this argument goes that leads to this proof, which is the following. Imagine applying an operator that creates a pair of anyons on top of the ground state, some open line. And we know that this line is deformable. It's only the endpoints that matter, where the rest of the line doesn't matter. Like any two lines with the same endpoints, they create the same excitation. And what you can show is that if you also assume that the system was short-range entangled, then this would mean, together with this deformability, that there is also some local operator that just creates an individual anion. That you could replace the string with just two operators whose size is kind of proportional to t that create individual anions. And you can easily see that this is inconsistent with having any non-trivial braiding, because then I try to braid some other anion around this excitation, but it has no way of saying that this excitation is there. It cannot have any non-trivial braiding. So the upshot of this argument is that if I have point-like anions with non-trivial braiding, it must mean that there is some long-range entanglement in the state. Okay, so this was all about ground state phases. What about finite temperatures? And as I mentioned at the beginning, it's kind of well known that if I go to finite temperatures and take the 2D toric code, or actually is known rigorously for a large family of two-dimensional phases, it immediately becomes trivial. It's no longer in a non-trivial phase. And the picture for this is that these point-like anion excitations, they immediately proliferate. You immediately get them all over the system, kind of destroying any non-trivial order. And you can think of this as kind of similar to why there is no spontaneous symmetry breaking in one dimension. If you think about the one-dimensional Ising model, domain walls are point-like excitations, they also proliferate immediately at any finite temperature. And the reason for this is the kind of usual energy entropy argument. There's an order 1 energy cost of creating an excitation, but you can put it anywhere in the system. So there's a logarithmic in system size entropy gain. So entropy always wins over energy. And that's why these are things kind of proliferate immediately. And so this is about finite temperatures. But if you think about these sort of synthetic systems that I mentioned, there's actually a similar issue there. That if you have any amount of noise, if you allow the noise to act for long enough, it also will lead to this proliferation that destroys your order. But this picture, this analogy with the Ising model also suggests a way out, which is to go to higher dimensions. Just as in the Ising model, if I go from 1D to 2D, I now do have a thermally stable symmetry broken state. I can do something like this here. But the unfortunate thing is I have to go to 4 dimensions. There's a version of the toric code in 4 dimensions, where what happens is that I still have 2 types of excitations, E and M, but now they are both not point-like excitations, but extended loop-like excitations. Kind of like how domain walls in the Ising model become loops in higher dimensions or in 2 dimensions. And this leads to a thermal stability. Now, this is a state that survives at finite temperatures until some critical temperature. And there are different properties that you can establish at low enough temperatures. One is that this is something that you can use as a passive quantum memory, and I'll explain what that means in the next slide. But the other one is that this long-range entanglement survives, that your thermal state at low temperatures still has this non-trivial long-range quantum correlation. And to define that, you have to think a little bit about what that actually means for a mixed state. So I told you what a short-range entangled pure state is. Now I can define a short-range entangled mixed state as something that I can create as a statistical mixture of short-range entangled pure states. Yeah. That's right. I mean, in the sort of strict sense of taking a thermodynamic limit, that's true. At low enough temperatures, we have some large length scale where locally it sort of looks topologically ordered. So it's sort of, in some ways, it might look topologically ordered, but actually, if you do things rigorously, take a thermodynamic limit, then it's not topologically ordered at any finite temperature. Okay, so I will take this as my definition of topological order at finite temperature, that the finite temperature state, eta minus beta h, cannot be written as a mixture of short-range entangled quantum states. And I will show that there is some example in 3D that establishes this. But before I do that, let me just kind of briefly make a detour and explain what I mean by this classical versus quantum memory that I mentioned. And it's easiest to understand it first in the case of a classical memory. So you could imagine taking a 2-dimensional Ising model, preparing it in 2 different ground states, one with positive and one with negative magnetization. Yes.
So basically, if you have a topological order phi and you increase the temperature, then basically in the sum, it should be the ground state. Then it should be long range from the beginning, right?
So these, I'm not specifying what these states are. I'm just defining what I mean by something being long range entangled. I'm defining it as, or defining it what I mean by short range entangled. Right. Short range entangled is something that I can write as a mixture of pure states.
Yeah, but if you take the formula applying density of state in this way, then basically the ground state will be in this sum, and the ground state will be long range.
That's right.
Right. So does that mean even at finite temperature is still?
Yeah. So right. Well, two comments. So one thing is that you can write eta minus beta h in this eigenbasis, and it will contain a ground state. But it's one thing in a giant sum. The sum will be dominated by states the finite energy density very far away from the ground state. So the ground state property doesn't imply much.
I have like approximation over there.
The other thing is that when you write a state as a sum, as a mixture, that's not unique. So the statement I want here is that there's no way of writing it like a mixture like this. There might be a state which we can both write as a mixture of long-range entangled state and as a mixture of short-range entangled state. I would still call that short-range entangled. Okay. Yeah. Depends on what you mean by correlation. So the model is still a kind of has zero correlation length. It's still a kind of a stabilizer model with zero correlation lengths. The key feature is really that your excitations are loops, so that I'll get back to this later, but basically you have to create a large loop, and then this energy entropy trade-off is now different than for point-like particles. Okay, so again, this is a bit of a detour, but yeah, so I mentioned this notion of memory, so I should explain what I mean. And I'm having in mind this kind of thought experiment where you take a system, prepare it in one of its ground states, and then you couple it to a thermal bath at some low temperature and see what happens. And for example, in a ferromagnet, I could take two different initial states with opposite magnetizations, couple to a bath, let it develop for a very long time, and it would still stay distinct. I could come back a day later, measure the magnetization, and I would still know which of these two states I started with. So I'm preserving kind of one bit of memory of the initial state, this magnetization being up or down. But this is really only a classical memory. If I prepared an initial state that was some superposition of two different magnetizations, the relative phase between those would not be preserved. That's very easy to be measured locally, and it's destroyed by coupling to an environment. So that's only a classical memory. And now what this 4D toric code achieves is a kind of quantum memory where you have multiple ground states, but you could take any of the ground states, any superposition, and take two of them, which are orthogonal, then they remain kind of distinguishable for a very long time when you couple to a low temperature bath. Okay, so there's some coherent version of a memory where the relative phase between the different ground states is also preserved. Okay? So in the 4D toric code, both of these things are achieved. You both have this passive quantum memory and you have long-range entanglement. But it requires to go to 4D, so the question is, what can you achieve if you are only in 3 dimensions? And this is what the rest of the talk will be about. Any other questions so far? Yeah. Well, so this is kind of the deconfined phase of this. You can think of this as a kind of Z2 gauge theory, but it's not the usual Z2 gauge theory. It's like, I mean, you would. So okay, so here I'm just talking about some sort of fixed point limit. Now I could add a perturbation, and I could drive a transition, like a confinement transition, and you could detect that confinement transition by some area to volume law like change. So that's true. And well, at 0 temperature, I'm a bit less sure what exactly happens at finite temperature. Yeah. Yes, I mean, so the fast thermalization is related to this memory aspect. Basically, having a memory means that you don't quickly thermalize. And yes, I agree that in principle, in that case, you should, I don't know if you should or could, but you could look at the thing that you actually thermalize to, which is some restricted version into like one of the sectors of your Gibbs state. Well, I think it's more like, if you have a memory, then you can kind of resolve this rho beta into different sectors, and you can ask for each sector, is it long-range entangled? I guess that's not something we checked explicitly, but I believe that generally. Well, I guess what I would say is that even when the system doesn't thermalize to e to the minus beta h itself, it usually thermalizes to something that looks like e to the minus beta h, kind of restricted to like a particular sector of the Hilbert space. And I think typically, if one is kind of long-range entangled, you would expect the other to also be long-range entangled. Yeah. Okay. So like those are not unrelated. Whether one or the other is long-range entangles, I would maybe can get back to that offline, but. Well, the 2D toric code actually would thermalize quickly. Like that would actually thermalize as fast as basically possible. It's basically if you don't thermalize quickly, that's kind of a sign usually that you're in a non-trivial phase already. Yeah, basically when you have loop-like excitations, then you tend to have a long thermalization time, because in order to really thermalize, you kind of have to create some large loop, like stretch it through the whole system, which is very energetically costly, and that takes kind of a long time if you are doing sort of thermodynamics. It's believed to be. I think, you can, it's not rigorously shown, but I think you can probably show it somewhere near the fixed point, and then it's believed to be true everywhere in the phase. Okay, good. So moving on. So rest of the talk will be about what happens in 3 dimensions. And it will be useful to first talk about something that doesn't work, and then why it doesn't work will kind of give us a hint of how to fix it. So the simplest thing you can look at in 3 dimensions is just the sort of naive generalization of the toric code to 3D. So now we have a 3-dimensional cubic lattice, qubits living on the edges, still qubits. You have Pauli X and Z operators. And I can define, again, a vertex term and plaquette terms. So vertex is now a product of 6 edges around the vertex. The plaquettes are products of 4 terms around the plaquette, but there are 3 differently oriented plaquettes. Okay? And these still all commute with each other. This is a exactly solvable stabilizer model. And it's sort of similar to a 2D case with some changes. So you still have 2 symmetries. You still have this kind of loop-like symmetry of a closed loop of a product of z's in the lattice. But your other symmetry, your X-type symmetry, is now not a loop, but a surface. I have to take a closed surface on the dual lattice, take a product of x's along the closed surface, and that commutes with the Hamiltonian and is generated by these vertex terms. But these 2, they still have a mixed anomaly, which you can see by the fact that they locally anti-commute, where a loop pierces a surface, you pick up a -1 from an X and a Z anti-commuting. And the consequence of that is that there's still some notion of a non-trivial braiding. Now it's a braiding of a loop with a point-like particle. I can take E anion, which I get by opening up a Z loop and have 2 endpoints, and braid it around a loop-like excitation, which I get at the boundary of an open surface or an open membrane of X's. And when I braid this point around this loop, I now pick up a minus sign, so there's some non-trivial braiding similar to what we had in 2D as a sign of this kind of mixed anomaly. And again, this implies a similar sort of topological order at t equals 0. For example, it implies that we have this long-range entanglement in the ground state. But what happens at finite temperature is that now we still have this issue of the proliferating excitations, that the point-like excitations, they immediately proliferate for the same reason as before, and they destroy one of the symmetries, that this kind of M surface symmetry is no longer well-defined at finite temperature. On the other hand, we did gain something. These loop-like excitations, as was mentioned before, these now no longer proliferate immediately. They only proliferate at some finite critical temperature, Tc. Below Tc, the typical loops you see in the thermal state, they are pretty small. They're kind of logarithmic in systems. You do have a kind of critical point here. But if you look at what happens below the critical point, there is a non-trivial phase there, but it's a fully classical phase. There is nothing quantum about it. And this has to do with the fact that the point-like excitations have proliferated. So one way of saying that this is not quantum is that if you try to do this memory experiment I described, you only get a classical memory. You can't really, you have like a preferred basis, but if you try to take a superposition of basis states and the ground states, the relative phase is not preserved. But you can also see that you don't have this kind of long-range entanglement that I talked about. And there's a nice argument for this statement due to Hastings, which is the following. So what Hastings noticed is that for these kinds of stabilizer Hamiltonians, where all terms commute, they all square to 1. If you think about the thermal state at finite temperatures, e to the minus beta h, then you can always write it as a mixture of the ground states of a family of slightly modified Hamiltonians. And these modified Hamiltonians are what you get if you start dropping terms from the original Hamiltonian. So I take this Hamiltonian, which is the sum of local terms, and now I add a coefficient, which can be 0 or 1 in front of each term. If this coefficient is 0, then I kind of drop one term. And you can think of this as kind of physically like punching holes in the system, that instead of taking a torus or a 2D plane, it's now a 2D plane with little holes in it. And now the question you need to understand is, what do the ground states of these Hamiltonians with holes in them look like? Are they short-range entangled? If they are, then it shows that, that your thermal state also has to be short-range entangled. And what Hastings showed is that indeed, you can disentangle the state with a circuit whose depth is only proportional to the typical distance between the holes. So, of course, you have a distribution over different holes, but this thermal state will be dominated by certain configurations of holes for entropic reasons. In particular, it will be dominated by configurations where the typical distance between holes is only logarithmic in system size, it's pretty small. And then there is a circuit whose depth is only this log L that will turn the ground state of this modified Hamiltonian into a trivial product state. And the physical picture for this is kind of nice. You can think of these holes as kind of hosting some condensate of your point like E anyons, which is a trivial phase. And then you use this circuit to sort of grow these condensates until they all merge into one big trivial phase. You do something like this. And what this shows is that there is a short-range circuit to disentangle, which means that your state is actually trivial. It has no long-range quantum entanglement at finite. Okay, so this attempt to do 3D topological order using just a simple toric code, it failed. Question is, can we avoid this? Can we fix somehow this argument? And I'll now show you how to do this. So here's a different Hamiltonian, which is called the 3D fermionic toric code. And the fermion will refer to the emergent quasiparticles. The actual microscopic Hilbert space is still only contains spin 1/2 degrees of freedom, or qubits. It's the same Hilbert space as the previous Hamiltonian. In fact, the vertex term will be the same as before. It doesn't need to change. But what we do is we change the plaquette terms slightly. Now, instead of a plaquette only containing product of 6 Pauli Z's along a plaquette, it will be a product of 4 Pauli Z's along a plaquette. It is now a product of 6 Pauli operators, 4 Z's and 2 X's, where the X's are on edges kind of sticking out of the plane of the plaquette. Okay? But you can still check that actually all these terms still commute. This is still a commuting stabilizer Hamiltonian. So now what happens to the symmetries? So the surface symmetry that we had, which was generated by the vertex term, is unchanged. Product of X's along the closed surface on the dual lattice is still a symmetry. Yeah. Oh, like how you map this thing to the original toric code, the 3D toric code? I'm not sure. I'm sure you could do it, but I haven't thought of that. It's just, you can just write it down and analyze it. But yeah, probably there is some sort of duality transformation that would relate this to. I have not thought about that. Okay, so my surface symmetry is the same as before, but this sort of loop symmetry I had is now different. Because now to get a loop symmetry, I have to construct it out of these plaquettes. So what I get is I get a closed loop of product of Z's on the lattice, but it is kind of hairy loop. It has this sort of little Pauli X's sticking out of it. So it's a different operator than before. And what one can show is that this makes a very important difference. Previously, we only had a kind of mixed anomaly between these two symmetries. Like the two symmetries together, they had an anomaly. And as you heard before, you can think of that as something like you can't gauge both of these simultaneously. You can gauge one or the other, but not both. But now, if you analyze this modified Z-tool operator with the hair, it turns out that this has an anomaly with itself, just by itself as an anomaly, without thinking about the other symmetry. Like you cannot consistently gauge this mu Z2 symmetry. Yeah, that's closely related to the fact that you cannot condense the excitations, because the most physical way to think about this anomaly is by thinking about braiding of the excitations. So previously we had some non-trivial braiding between the sort of vortex loops created by the X membrane and the endpoints of a line. But now it turns out that if you look at the endpoints of a line, sort of hairy line, these themselves have a non-trivial braiding. In particular, if you exchange two of them, they pick up a -1. So now the excitations created by these are fermions, which is a manifestation of this self-anomaly, which indeed means that they cannot be condensed. And this is kind of why the previous argument fails. I gave you this argument why you cannot have long-range entanglement at finite temperature, but it relied on the idea that you can create a condensed set of point-like excitations that you can then grow and merge. But here now these are fermions, you cannot condense fermions. So this argument fails. And what that means is that this could possibly have long-range entanglement at finite temperature. And what we showed is that indeed it does, that we can prove that at sufficiently low temperatures, below some Tc, if you look at e to the minus beta h, this is a state that does have long-range entanglement. In this definition that I gave, which is that you cannot write it as a statistical mixture of short-range entangled pure states. The ground state degeneracy, so I mean, it is also topologically ordered at 0 temperature. Don't quote me on that. I think it's the same degeneracy as the usual toric code in terms of like you just look at the number. It's a different topological order, but because it has different kinds of excitations, but it's the same degeneracy, I think. Yeah. No, well, again, so there are no fermions microscopically, like the Hilbert space is just qubits. Like the fermions are emergent quasi-particles. The actual microscopic Hilbert. No, so yeah, that's important. That's a confusing thing. Like when I say fermionic toric code, that's a statement about what the quasi-particles are, but microscopically, it's a qubit system. That's a good question. I'm not sure. Even if you could, it would not be stable at finite temperature, as I will explain. Yeah, so that secretly you are still using something about 3D, as I will explain in a moment. But probably there is a 2D version, but yeah, I have. Well, it's really a combination of two things. Is the point-like excitations being fermionic, but it's actually also important that there is the other excitations, which are loops, which stay small. Sorry? That they are loop-like and they stay small. So kind of you need both. And yes, the reason you need both is kind of the following. That, okay, so the statement we show is sort of similar to what I mentioned before, is that if you take any short-range entangled mixed state, then the fidelity with the thermal state, which is kind of the mixed state generalization of the notion of an overlap of two states, is exponentially small, or more precisely, it's kind of small, decays faster than any polynomial with system size, if the state is really short-range entangled. And the way we show this is the following. There's kind of a two-step argument. So here's an outline, and I'll have a bit more detail on the next slide. So what you need to do is the following. You have to start with your thermal state, which looks like this. It's a proliferation of the point-like excitations that are everywhere, but the loop-like excitations are small. And what you need to do is you first need to somehow clean up these loops. You have to deform your state to a new state where there are actually no loop-like excitation. And it's important because actually it's this latter state without the loop-like excitations that we can prove is long-range entangled. And that follows from kind of a similar type of argument, like the one I showed before about I have I have these things that braid non-trivially, and that's kind of inconsistent with being short-range entangled. And then what you have to argue is that if this new state you get after removing all the loops is long-range entangled, then the state you started with also has to be long-range entangled. And the way you argue that is a key point in that is that this process that gets rid of the loops has to be local, that you can kind of do some local operation that gets rid of the loops, and that requires the loops to be small. Like you're really using the fact that the loops are small, so you can kind of just locally remove them without changing the long-range structure of correlation. Okay, so here is how the argument works in a bit more detail. So you can consider a mixed state which has this kind of fermion loop symmetry, that you are multiplying it from the left with this closed loop that I showed before, and it leaves the state invariant. So this is an example of what Abhinav described as a strong symmetry. There's this distinction between strong and weak symmetries. So this would be a state that has a strong one-form symmetry under this kind of F-loop symmetry. Physically, it means that if I write as a mixture, all the pure states are individually symmetric. And then for a state with this property, you can kind of generalize this argument I gave before for the toric code very easily to show that the fact that the endpoints of this F-loop have a non-trivial braiding is inconsistent with being short-range entangled, and that fidelity with any short-range entangled state has to be kind of exponentially small. Indeed. Okay, so that's nice, but the thermal state that we are looking at, that we're interested in, is actually not a state that has this property. It's not invariant under the fermion loop as a strong symmetry. And the reason for that has to do with the fact that you do have these loop-like vortex excitations. And because there is a non-trivial braiding between the F loop, which is a word line of a fermion, and these vortex loops, if I look at this F loop, it picks up a minus sign whenever it sort of winds around or links non-trivially with the vortex loop. And since there is a bunch of small vortex loops, I actually pick up something that's not 1, which I would require for this, but something that goes to 0 as I make this loop very big. So actually, the state I have does not have this strong symmetry. But what I can do is kind of deform it in a way that restores the symmetry. So I have to deform the state, get rid of all the vortex loops, the excitations, to get a new state which now does have this strong symmetry condition. And there are various ways of doing that, but one way that we describe is something like the following, where you can imagine cutting your system up into a bunch of patches. And then in each patch, if you have a loop that's kind of entirely within the patch, you sort of know how to get rid of it. Like if you know what's inside and outside, so you can contract it to 0 and get rid of it. And then you can do this kind of moving these patches around in 4 steps. And then at the end of that, you get rid of all loops, except those that are kind of larger than the size of these patches, that kind of stretch through multiple patches that you don't remove. And now you can use this fact that at low enough temperature, almost all the loops that you see have a size that's only logarithmic in system size. So if I choose the size of the patches to be larger than that, then I'm good. Then I basically removed almost all the loops. So in particular, you can make the size of the patches to be log L squared, that's big enough, that you can show that if I apply this operation to my thermal state, I get a state with no loops up to some error that's like exponentially small in the size of patches, which is basically almost exponentially small in the system size. Or sorry, no, I shouldn't say that, but it's decays faster than any polynomial in the system size. Okay, so this is some kind of quantum channel that gets rid of the loops. And important, it's a local quantum channel. It only changes stuff within this log L squared length scale. It doesn't change anything about the state on kind of larger length scale. And the second step of the argument is to show that there's something called the data processing inequality that tells you that when I apply a quantum channel, if I take 2 states, apply a quantum channel to both of them, they can only get closer to each other. Or in terms of the fidelity, their fidelity can only increase. So the fidelity of rho beta with any short-range entangled state is upper bounded by what I get if I apply this operation to both states. And then I end up with this loopless state, which has this strong symmetry condition. And because this channel I applied was local, if I apply it to a short-range entangled state, the resulting state I get still short-range entangled. So if I kind of combine these two statements, I get that the final state I get after cleaning up the loops has to be far from any short-range entangled state. On the other hand, because of the locality of this process, the initial state also had to be far from all short-range entangled states. And I have to add up these two error terms that I encounter, but both of these kind of decay very quickly in system size, faster than a polynomial. Yes, so, okay, so the critical temperature from this, it basically corresponds to the point where these loops proliferate, when the typical size of loops is no longer log L, but becomes kind of comparable to the system size. And one can kind of bound that of what that is in this model. Yeah, so I guess in our argument, we have a bound on a critical temperature for this. We also know that there is an actual thermal phase transition in this model where this loop proliferation happens. Those are not the same temperature, they are pretty close, but that's probably just that just has to do with the way we prove things. We believe that actually all the way to the actual physical critical temperature, this would actually work. And that's the same thing as like a 3D. The critical temperature is the same as you had in the original 3D toric code. Okay, so this is my last slide. Is that you end up with this phase diagram where again the loop proliferation happens at some finite TC. Below that there is a non-trivial phase, but now it's still only a classical memory, similar to the previous bosonic 3D toric code, and that has to do with the fact that the point-like excitations have proliferated immediately at finite temperature. But because they were fermions, actually the state you end up with now has long-range entanglement. So that was the statement we wanted to prove. Okay, so I'll just leave up this summary slide and mention there are two interesting outlying questions about this, which is one is going from this kind of simple toy model to something more realistic that might actually be maybe only has like two-body interactions so that you can, but it's still in the same phase so that you can hope to engineer it in some actual experiment and then to actually look for those experiments and to ask also, how would you diagnose if you actually had this phase? Like I gave you kind of a formal definition and a proof, but like what experiments would you do, or even just numerical experiments, like what quantity would tell you that you are in this phase, are all kind of interesting open questions. Okay, so that's all I want to say, and thank you for your attention.
So the key ingredient seems to be that the point-like excitations are fermionic.
That's right.
And somehow this is not possible in 2D.
Well, no. Okay. So again, it's a combination of two things. It's the fact that the excitations are fermionic, but it's also the fact that the other excitations were loops was important because you needed to. So when you go in terms of symmetries, like this symmetry is destroyed when you go to finite temperature, and the question is, can you kind of locally restore it? And it turns out that whether you can locally restore it or not, that has to do with the fact that the other excitations have not proliferated.
Maybe one quick question and then.
So maybe you mentioned it, but could you tell how is it related to intrinsic topological order and also realization of weak and strong symmetry breaking?
Right. So it's okay. So you still have this kind of two symmetries here. You have the sort of loop and the surface symmetry. And if you look at the thermal state, it has both of these as weak symmetries because they commute with the Hamiltonian. But as Abhinav explained, if you only have weak symmetries, that doesn't actually tell you anything. The key point is that the loop symmetry, even though it's not an exact strong symmetry, it's kind of an emergent strong symmetry. And the way you quantify that is by this process where you can like clean the loops and get a different state which does have an exact one-form symmetry, a strong one-form symmetry that's kind of locally related to the state that you started with. And then it's kind of this, and then the thing you have is kind of an example of an intrinsically mixed topological phase with a sort of added twist that it's the symmetries that show up. One of the symmetries is an emergent symmetry, not an exact symmetry.
So I'm confused. So they are emergent, but how are they realized? You said both of them are strong? Or
No, one is strong. One is strong. The other is weak.
okay. That's why it's intrinsic, right? So
Yes.
thank you.
One more question.
No, I don't think so. Like I don't. That just gives you 4 bits of classical information. Unless you do something else, just 2 copies will not buy you much.
Okay. Thanks him one more time and
Thank you.